Okay, I hope you can see my screen. I can see it in the monitor at the moment. So thank you very much. Today we're going to talk about smart maintenance. And this is a small outline of the presentation. We'll start with predictive maintenance in Industry 4.0 and why it is important. Then we'll go over smart maintenance enabled by intelligent manufacturing technologies and what this concept entails in general. And then we will go over to the technologies and how we can use them to start the process of building a chain and an architecture of smart maintenance. So we will talk about Internet of Things and how it allows us to transfer data. We will talk about predictive analytics. We will go over to digital maintenance assistance and how this particular context-sensitive assistance can be used for smart maintenance activities. There was some example of product service systems, smart services, and then in the end, network production. So first, predictive maintenance in Industry 4.0. Why it is important? Well, it's a cost-saving measure. The potential costs in maintenance, repair, and overhaul through Industry 4.0 are between 20 to 30%. And according to IDC, it will help the industry save up to 50% of maintenance costs by 2022. And according to VDMA, which is the Association of Mechanical Engineering here, and Holland Berger, predictive maintenance is recognized as a key factor in the producing industry. I'm getting feedback that my microphone is cutting. Please allow me a second to see if I can correct that. I hope that this is better at the moment. The last part, that the cost for maintenance and inspection and unplanned repair account for 46% of the operating cost of a machine tool. So by using smart maintenance or predictive maintenance, we can greatly reduce these costs that are appearing in the production. Now, let's see the concept of smart maintenance. So we're talking about integrated smart maintenance concepts for machine tools and how this works. Please let me know if you can hear the sound of the video. Okay. Okay. I'm informed that this video doesn't work, but I can essentially explain what it says. The idea is that we integrate sensors into machinery, and then we're using digital assistance apps to inform the stakeholders. So in this case, it would be a shift supervisor or a service technician, that the data coming from the sensors are showing that we have degradation on the machine components. So if the machine isn't working correctly, then we can start a maintenance process. And through this assistance, we can save the data of the maintenance process so that the rest of the stakeholders are also informed that the production can continue as planned and as wished. And this concept is enabled by the technologies that you can see in the video. So on the one hand, we have the sensors that are attached on the machine, and they send data through an IoT device to a computer, where the information is then analyzed, and through machine learning, we can decide what we need to do. In the next slide, we can see here the architecture that we are using. So here is the machine with the sensors, and here is an edge device. On this edge device, there is an AI running on the background, so a neural network or other machine learning algorithms. And from there, the result, along with the raw data, is being sent to an IoT platform. And on this from this IoT platform, we can A, inform the stakeholders through the digital assistants, as I said, B, save them onto a database so that we can create what we call a life cycle database of the machine and the components, and C, display the data on a dashboard so that the stakeholders can see what's happening in real time. So if the shift supervisor wants to check the status of the machine and how the production is running, they are able to do so through the dashboard. And through the combination of all those things, we can make predictions about the components in the future. So based on the history that we have on the lifecycle database, we can calculate the remaining useful life of these components. Now into a bit more detail. Let's start with IoT. So we're talking about the development of IoT architectures and pipelines. This is the basis on which we are building the whole concept of smart maintenance. So we are retrofitting machines with sensors in case they're not able to send data by themselves. And then we design the data pipelines for the analysis. So after the data is being sent, we are in a position to create virtual representations of the machines and the components, so-called digital twins, using asset administration shells. These asset administration shells are essentially a standardized way of describing an asset that exists in the physical world in the digital twin. And through this process, we can combine these heterogeneous data sources because if you can imagine, we are talking about data coming from the PLC or from an accelerometer or another sensor that's being used on the machine, or we are having even more data sources like the digital maintenance systems. So when we try to combine those, the interfaces can be complicated, but through this architecture, we are in a position to do that quite easily. So this is the basis for the development of the data-driven business models that we want to use because predictive maintenance is data-driven essentially. And through that, we enable standardized access to data for everyone in the production that wants to have this. And we prepare the system for use-dependent or case-dependent analysis of the data. The next step would be predictive analytics. In this case, we're talking about intelligent degradation, plant and process monitoring. So through this IoT-based networking of systems and cloud services with the sensor networks, we can do condition monitoring to support maintenance. This is a real-time evaluation of the processes and of the data that is coming from the sensors. To that, we add the context-sensitive process support through the mobile assistance systems that we saw before. And then we integrate the historical data from the machines and the components. And through the development of application-related digital twins, we can have a holistic solution and a holistic system that can work in our favor to reduce the downtime and increase the reliability in our production. The second point is the increased efficiency of maintenance measures because we perform them when before a component is completely broken down and before the production stops. And we have data transparency through the traceability and documentation because everything that is happening in the maintenance process is saved on this database. And as the colleague said before, there are multiple solutions of sensors, MEM sensors as well. We are using them to have a cost-effective Industry 4.0 retrofit for existing plants. And into a bit more detail of the analysis algorithm, so we use machine learning-based classifiers for the intelligent signal pre-processing and of course, the classification on the sensor node or the edge device based on the architecture that we want to develop. Based on that, we can detect irregularities and damages of the in the operation of a machine, and we can calculate the remaining useful life and evaluate it based on the models that we have created. And through the cloud and IoT platform integration, this data is also saved on the digital twin representation that we have. So a very important aspect of smart maintenance of our concept is the digital maintenance assistant. So this context-sensitive assistance follows a model-based approach. The logic of a workflow is mapped in a process model, as you can see on the right side of the slide, where the states describe start and end of the process steps, and then the actions contain information flow and a style sheet. And the resources provide interfaces for machine-to-machine communication based on the protocol that we have, and the content elements for its visualization. The entire model, after it's created, is being converted to a JSON format. And from that, we have a graphical or visualized user interface that is generated from the JSON file. And the UI is then used on a mobile device based on the needs of the factory or the production. And the information about the proceeded steps is transferred to a cloud server. So how do these points communicate with each other? Where we have a linkage to an IoT platform. The smart machine, through the sensors and the IoT pipeline, sends information, and the IoT platform then hosts information about A, the maintained products, so the digital twins, B, the steps of the general maintenance process, so the process models that we have saved, and there is a linkage or an interface of the general process model and the actual component. So what is happening in each process, which component is being changed, what the service case is, and so on. And then we have further information about the actual service case, who performed it, when it was performed, the new components that were used, from whom they were sent, and so on. And of course, this information or these concepts can be used for other aspects as well. So in here, if we're talking about the automotive industry, we're talking about a product service system where we integrate the product with the service solution, and we have monitoring and prediction with analytics. We are able to collect data on vehicle use and load. And then through the cloud connection, we can save the data and have a data management platform and a database for it. At the same time, we have vehicle and fleet analytics, where based on the condition, we receive notifications, including a forecast of necessary maintenance or services of the individual components that are equipped with the sensors. And all that is being sent to a device. So we have an app connection, very similar to the digital maintenance assistant, so a context-sensitive application as well, through which we are in a position to increase the availability and reliability of products and or vehicles. We have an increased customer satisfaction through the transparency and planability, and optimal utilization through fleet analytics in case of car sharing, which at least in Berlin is very popular, I hear, in Brazil as well. And this approach is benefit-oriented and cost-efficient because we can design the next generation of the products based on the usage data that we have. Same thing about smart services. So this is more personalized mobility through the intelligent analysis of data. The data is being fed to a mobile dashboard. We can create user-specific profiles for comfort and or driving experience. And the car sharing information is also being sent, where a price adjustment based on the usage and the individual customer can be adapted. Again, we have enhanced customer experience, increased driver safety, and cost reduction. And the last point, most of this data is quite critical and quite sensitive. So through the use of blockchain technology and the public Ethereum blockchain, we can have a reliable and efficient networking of production facilities. The idea is that we have a cross-company networking of production facilities and ERP systems. So the information that's being fed comes from, for example, the tool manufacturer or the OEM or the supplier, and it's all part of the smart contract of blockchain. The connection of the plant is happening through an OPC-UA server, and then the communication machine to machine is happening through an MQTT protocol. And the synchronization of the machine control, so the PLC and the SAP, is happening through the blockchain, through the Ethereum blockchain. And as a result, there is no disclosure of sensitive process data through the zero knowledge evidence on which blockchain technology is based. And as a result, we have data security and transparency in all automated ordering processes, and not only, we can adapt it for all processes within a production as well. Thank you very much for your attention. Are there any questions?